Okay, for this section, we're going to start seeing how the vectors we just studied are going to blend into our calculus goals for the semester. So we're going to start looking at how we can do things with vectors and functions together. So let's start with recalling that in calculus class, not whether one or two depends on where you took the class, you learn that the curve and the plane can be represented in terms of parametric equations. Sometimes this is very useful if you have some curve that isn't given by a function, like the unit circle, which we'll look at in a moment, then we can still represent this nicely in terms of equations, um, even though it's not a function. So for example, the unit circle we've seen before can be represented by points cosine t sine t, where 0 is between or t is between 0 and 2 pi. So this is a nice way to represent the unit circle. So here's a picture of this. So we just see the angle t here. We go to that angle from the x-axis, and that gives us our point cosine t sine t. So if we think of this, we could form a triangle here with this, and the cosine t is our x value, the sine t is our y value. So that's how we get the cosine t sine t for the unit circle. But now what we can do is, instead of just looking at this parameterization in the form x of t and y of t, we're going to use what are called vector-valued functions to parameterize our curve. So we'll eventually look at more than one variable vector-valued functions, but for now, a one-variable vector-valued function, r of t, this is a function that inputs a number t and it outputs a vector r of t. So notice the r here is bold to indicate this is actually a vector that's getting output. So we've had before lots of times we input a number and we output a number, and that's just a regular function. And we've also seen we can have functions where we input many variables and output a number. But now we're looking at inputting a number and outputting a vector. So at first, when we'll just start with vectors in the plane, this will look like r of t is equal to x of ti plus y of tj. So notice the x of t is the x component, the y of t is the j component of our vector. So if we take this vector r of t and we put its starting point at the origin, well, then the tip of the vector will be at the point x of t, y of t. So this r of t, if we think of the tips of the tips of the vector are going along our curve that we parameterized up here. So we can kind of think of this vector r of t as tracing out the curve as we change the values of t. So let's see how this works with the unit circle, and now we'll do this with vectors. So we're going to take our equation, or our parameterization for the circle, which was cosine t sine t, and we're going to put those in terms of our vector now. So we have the vector r of t as cosine ti sine tj for 0 less than or equal to t less than or equal to 2 pi. So if I plug in t equals 0, I have cosine of 0I, which is just I, plus sine of 0 j, and so sine of 0 is 0. So r of 0 is just the vector I. So we see we have this pictured here. So r of 0 is just this vector I. So it traces out, if we think of the tip of this as just at the point 1, 0. So it's this point 1, 0 on our curve, unit circle here. And so if we look at r as, say, pi over 6 here, well, cosine of pi over 6 is square root of 3 over 2, and sine of pi over 6 is 1/2. So our vector r of pi over 6 is square root of 3 over 2i plus 1/2 j. And so that's this vector that we've pictured here. And so the point here at the tip is square root of 3 over 2 comma 1/2. And one more example, if we do r of pi over 4, cosine and sine of pi over 4 are both square root of 2 over 2. So we get this vector here, r of pi over 4, going out to the point square root of 2 over 2 comma square root of 2 over 2. And so we can continue to evaluate various values of t, and it's going to move along this circle. And each time, if we think of drawing say a point at the tip of the vector, and we draw all of the possible points, we'll get the unit circle. So let's see how this works with an animation. So we can see here, as I change my values of t, this vector is moving around the unit circle, and if I'm drawing a point at the tip of the vector each time t moves, I'm tracing out exactly this curve, the unit circle here. Okay, and so you can see if it stops there, we start over again, going around again. But this is just tracing out this curve, so we can think of the tips of these vectors as giving us the curve. So this r of t is actually giving us all the information we want for this curve, in this case the unit circle. So as you probably learned when you saw parametric curves before, parameterizing curves is a bit of an art form. There's no set method of this is what you do to parameterize a curve. The more of them you do, the better you'll get at them. There is one case that is particularly easy though. So if we want to parameterize a curve that is given by a function, so sometimes we will want this. So if we just have a function y equals f of x, we can always parameterize this by just letting t be equal to x, and then y is equal to f of t. So our parameterization in this case is r of t is equal to ti plus f of tj. So that case is always pretty easy. Now we can also consider our curves in 3-space. So in this case, our vector valued functions, they still input a variable t, but now we have 3 components to keep track of because we need to keep track of the z direction as well. So we have x of ti plus y of tj plus z of tk. And so just like regular graphs in 3-space, these are going to be harder to graph than curves in 2-space. But of course, we can use technology to do this to help us out a bit. Sometimes we can still graph them by hand as well for simple cases. So what we'll do here to end this lecture is we'll see how the vector valued function traces out a spiral in 3-space. So we're going to have our vector r of t. We'll see what the formula for that is. This is one that you could probably figure out how to graph by hand without technology, but this will show us how the vectors here are tracing out the curve in 3-space just like they did in 2-space before. So our vector valued function in this case, if I want a spiral, I'm going to want it to be a circle in terms of the I and the j, and then the value for z here, I put t over 3, and that was just to make the curve look a little nicer. We could use t, it would just be spread out a little bit more. But basically that t is going to make the z value change. So even though if we forgot about the k values, we'd just be graphing the unit circle again. Since we have that t component in the k direction, it's going to change our z value, so it's going to spiral up. So here's an animation of the vectors tracing out this curve. So you can see this pink curve is spiraling up. If you were to rotate this and look down, you'd just get the unit circle, but this z value is making it increase. We can see these vector value function, this arrow is our r of t, and it's tracing out our curve. If we think of wherever the arrow ends, we just draw a point at that arrow, at that end of the arrow, and then it gets this pink curve here, which is our spiral. So we'll be doing some more with graphing these and understanding what's going on with the vector valued functions here in terms of getting curves. But eventually we're going to use these curves to do calculus on. So that'll be what's coming up next.